Today we're talking about structural corruption. What it means when your data's structure is not just incomplete, not just fragmented, but internally wrong. We'll walk through what structural corruption actually looks like, why it's dangerous, how it differs from simple data errors, and how to detect, repair, and prevent it in real systems. Let's begin with a clear idea. Structure gives data integrity. It defines how records relate, what fields mean, what types they hold, and what constraints must always be true. Structural corruption happens when those structural guarantees are violated. When relationships point to the wrong entities, when keys no longer uniquely identify records, when constraints exist on paper but not in reality. And here's the important distinction. Normal data errors are about bad values. Structural corruption is about broken meaning. Imagine a user table where user ID is supposed to be unique. Due to a faulty migration, duplicate IDs are introduced. The data still looks valid, integers in the right column, but identity is corrupted. Joins now produce duplicated rows, analytics double count users, models overestimate engagement. Nothing crashes, but everything becomes subtly wrong. Or imagine foreign keys. An orders table references customer ID. Due to a faulty backfill, some orders now reference IDs that belong to a different region's customer table. Structurally, the column exists. Technically, the type matches, but the relational integrity is broken. That's structural corruption. Why does this happen? There are a few common causes. First, unsafe migrations, schema changes that alter keys, merge tables, or reassign identifiers without full reconciliation. Second, concurrent writes or race conditions that bypass constraints. Third, manual patches or ad hoc scripts that modify data directly in production. Fourth, cross-system synchronization errors, where two systems disagree about identity or ownership. And fifth, corruption introduced during serialization or transformation, especially when parsing or casting logic silently fails. What makes structural corruption especially dangerous is that it hides inside apparently valid data. Field names are present, types look correct, pipelines run successfully, dashboards update, but the internal relationships, the semantic glue, are broken. The consequences compound quickly. Duplicate keys break uniqueness assumptions. Broken foreign keys reduce join integrity. Misaligned hierarchies distort aggregations. And models trained on corrupted relationships learn patterns that don't exist. In many cases, teams only notice structural corruption when downstream metrics drift without obvious cause. So how do you detect it? You don't rely on surface-level schema checks. You test invariants. Monitor uniqueness constraints on identifiers, not just declared constraints, but actual runtime checks. Measure referential integrity. What percentage of foreign keys actually resolve? Track relationship consistency. For example, if a user belongs to one region, ensure their orders don't belong to another. Verify cardinality expectations. One-to-one relationships shouldn't suddenly become one-to-many. And run reconciliation jobs that compare aggregates across related tables. Lineage is critical here. When structural corruption appears, you need to trace which transformation introduced the inconsistency. Without lineage, debugging becomes guesswork. Now let's talk about repair. Structural corruption repair requires caution. Unlike missing fields, you can't simply replay ingestion and hope everything aligns. First, isolate the corrupted scope, identify affected records, time ranges, and downstream consumers. Second, reconstruct truth from authoritative sources, often upstream systems or backups. Third, rebuild keys and relationships carefully, validating invariants at each step. Fourth, rerun downstream computations, aggregates, features, models that depended on corrupted data. In severe cases, you may need to roll back to a snapshot and replay changes with corrected logic. The key principle is this: restore relationships before restoring confidence. Now, prevention. Structural corruption is best prevented with layered defenses. Enforce constraints at the storage layer whenever possible. Uniqueness, foreign keys, not null constraints. Add invariant checks in pipelines. Don't assume constraints are enforced elsewhere. Use idempotent rights and transactional guarantees to avoid race condition corruption. Version migrations and test them against production-like data before rollout. Implement contract testing between systems that exchange identifiers. Observability also matters. Surface integrity metrics alongside business metrics. Make referential integrity, duplicate rates and key consistency visible on dashboards, not buried in logs. And perhaps most importantly, assign ownership. Structural integrity requires someone accountable for core entities. When identity and relationships are everyone's responsibility, they're no one's responsibility. Let's step back for a moment. Structural corruption is not about messy data. It's about broken guarantees. It's when your data structure stops representing reality accurately, even though everything still looks fine. And that's why it's one of the most dangerous forms of data degradation. To wrap up, structural corruption violates identity and relationships. It hides inside valid-looking schemas. It spreads silently through joins and models. And it requires invariant monitoring, careful repair, and strong governance to prevent. If you take one thing away from today, don't just validate fields. Validate relationships, because structure is not just shape, it's meaning.